part 1 of my second Nerf turret. If you haven't seen the first video, I'd recommend you check it out. My first turret had a few different problems that I wanted to solve. It took very long to reload and could only hold 2 darts. The control loop used to lock onto target wasn't very good, and the camera struggled to detect faces in different lighting conditions. In this video, I solved the reload time and the dart capacity. Let's get started. My first bits of inspiration came from this dart shooter I got online. It has a large dart capacity and shoots darts using these 2 flywheels. I thought about just mounting this to a couple servos and calling it good, but I didn't like that idea for a few reasons. It's a bit bulky, doesn't have the fastest motors, and loading darts is a bit tedious. I took some notes, tossed it aside, and came up with this. My design has 6 main parts. It has 2 flywheels, an easy to load dart magazine, a magazine drive, magazine position sensors, a firing pin, and of course a microcontroller. Let's start with the flywheels. I could have used the 2 motors from this dart shooter, but they're pretty weak. I had these spare Emax motors laying around, so I decided to use these instead. Initially, I started with the motors by themselves, but I wanted a bit more speed. I decided to use flywheels to do this, with my first attempt being 3D printed. The wheels ended up being oblong and out of balance, so I stupidly spun the motor up and used a knife to try and remove some material and decrease the vibrations. Whoops. After that fun little mishap, I machined a couple of flywheels out of polycarbonate. One of the problems I saw with this dart shooter was loading the darts. To keep the darts in place, the designers closed off the back end and added this little wall to the front. To load the darts, you need to come in at an angle, which would be a bit tricky to do automatically. I wanted my magazine to be automatically loaded like my last turret, so I needed a different method for keeping the darts in place. This is what I ended up with. It has 4 chambers, 2 rails, 4 clamps, and this thing that I'll cover in a bit. Let me show you the clamps. There are 4 of these slices, each with its own clamp. Pushing and pulling on these clamps will clamp and unclamp the dart. To control this movement, I added these nubs to the clamp and made a rail for them to ride in. To show how the rail works, I made this cross section. As the magazine travels along the rail, the dart clamp gets pushed and pulled. On each end of the rail, there's a dip that pulls the clamp open. These dips are used to open up all the chambers when the magazine is in the left or right loading positions. This gives me the ability to easily load the darts and then immediately hold them in place by moving the magazine towards the center. I didn't want to immediately let go of each dart as it moved into the firing position, so instead of adding a dip in the center, I added this moving arm that will unclamp the dart. My first prototype was 3D printed vertically as one part. I did this to avoid cleaning out that pesky support material. Functionally it worked, but the thick layer lines caused a lot of friction and noise. Instead, I went with a multi-bodied part that I glued together. The result was much cleaner and quieter. I also added a bunch of this grease to make it run smoother. While I'm talking about this, I just need to point out how creepy this mascot is. Why is he so jacked?
Why is he looking at me like that?
Anyway, the unclamping arms are controlled by this tiny servo on the bottom. It ends up fitting together pretty well. Once I figured out the magazine, I had to figure out how to move it into position. My first idea was to use a timing belt like this and a mating timing belt on the magazine. The main problem with this design was how weak the motor is. The motor was barely able to move the belt through the tight bends and pulleys, so just about any external force would stall the motor. I was very limited with space, so it would have been difficult to make the design more rigid or add a bigger motor. My next idea was to essentially replace the timing belt with an O-ring and put grippy rubber on the magazine. The motor certainly was able to spin it with much less effort, but not much else about it worked. The next thought was to use a lead screw and this kind of half nut on the magazine. My first attempt didn't go super well, but it was definitely a step in the right direction. I had some issues with the magazine binding and the motor skipping, but with a few tweaks to the design and some more careful assembly, I was able to get it to work pretty well. This 3mm pitch wasn't quite as fast as I had wanted, so I changed the pitch to 6mm. I wanted some more speed, so I changed it again to 12mm. It still doesn't move as fast as I'd like it to, but with further friction reductions and lead screw changes, it will get faster. I'll save that for the future. I used magnets and Hall effect sensors on my previous turret. That worked pretty well because the sensors were always approached from the same direction. Magnets have a bubble-shaped magnetic field that these sensors pick up on, so you end up with a large sensing range that really decreases the accuracy, kind of like having a ruler with really thick marks. To try and get around this, I added this pin to redirect the magnetic field into a smaller area, effectively shrinking the bubble. It worked, but maybe a little bit too well. The pin really needs to be in the perfect spot, and I didn't think that these plastic parts were capable of being that accurate. Next, I tried using a through-beam sensor that would detect small holes in this plate. It worked pretty well, but these sensors take up a lot of space. The gap these sensors need to fit into is about 1/4 of an inch wide. Even removing these LEDs from their housing wouldn't shrink them down enough. My mind then went to fiber optics. The basic idea is to transmit light to a light sensor through a plastic or glass fiber. To turn this idea into a through-beam sensor, you just split the fiber in half. Doing this effectively shrinks the sensor from this to this. I started by collecting some data to see how well this idea would work. I hooked up this LED and photodiode and measured the output with the multimeter. When the sensor is fully saturated by a bright light, it will output 5 volts. The sensor outputs about 3.2 volts when exposed to the LED I plan on using. That's definitely workable. The voltage really drops off when I add the fiber optic to the loop. 0.8 volts is still pretty low, but certainly is still possible to detect. When I cut the fiber in half and moved it apart, the voltage really fell off a cliff. I was getting 10 millivolts here and 40 millivolts here. Definitely not great. This massive fall from 3.2 volts to 40 millivolts really proves how inefficient my setup is. A large reason for this was how much light didn't make it into the fiber. It was going to take a decent amount of work to get a reliable sensor from this, so I decided to keep it simple and use some limit switches. I found these switches and designed this housing to mount them. This may not be as interesting as magnets or fiber optics, but it's very simple and robust. I'm using 3 switches to know if the magazine is in one of the firing positions or one of the loading positions. To hit the switches, the magazine has 6 bumps. When one of these 4 bumps hit the center switch, the Pico knows that the magazine is ready to fire. When these other 2 bumps hit the outer switches, the Pico knows the magazine is ready to be loaded. From here you can see that the middle 4 and outer 2 bumps are offset so they don't interfere with each other. The last problem to solve was getting the dart out of the chamber and into the flywheels. There's too much distance to travel using a servo, so I needed something that could quickly hit the darts into the flywheels. I first tried to use a solenoid for its ability to move very quickly. It didn't work very well. I then settled with using a spring-loaded firing pin. My design uses a motor-driven cam that moves this lever out, compressing these 2 springs. The cam has a magnet embedded in it that passes over this Hall effect sensor. With this setup, I can theoretically fire at a rate of about 1 dart per second. In testing, I did find that the position of the dart relative to the striker was pretty important. If too far away or too close, the dart wouldn't get pushed far enough forward. To make sure this wasn't an issue, I added these lead-ins to the motor shroud and back standoff to guarantee that the darts are positioned correctly. Here's the firing pin hitting the darts into the flywheel. To double check if the darts have left the station, I added a through-beam sensor. If the darts don't get hit far enough, they'll block the sensor, and as soon as the dart reaches the flywheel, it'll get shot out and unblock the sensor. That way the system will know not to jam itself up when there's still a dart in the chamber, which certainly has never happened. Now that I had all the mechanical parts figured out, I moved on to the microcontroller. On my previous turret, everything on the pan and tilt was controlled by an Arduino Mega in the base. My new design has a lot more going on, so it made more sense to put the microcontroller directly on the turret. I went and looked at the microcontrollers I had laying around. The Mega that I used for my previous turret takes up a lot of space and is expensive. The next option was the Arduino Uno. This one also takes up too much space, but is not as expensive. The next option was a Nano. It's the perfect size, but I've had issues connecting with these knockoff boards in the past. The name brand Arduino Nano also cost a surprising amount, and I have a history of burning up these boards. My last option was the Raspberry Pi Pico. It is the best of all worlds. It is very compact, has a lot of flexible I/O, and best of all, $4. We got a winner. Once I had picked the microcontroller, I went to work with breadboarding. Right here is the Raspberry Pi Pico. Next to it is a logic level shifter that converts the 5 volt signal from the sensors into a 3.3 volt signal for the Pico. Right next to that is a DC motor controller for the magazine and spring motors. These are 2 limit switches I've been using for testing. Up here are the voltage converters that step down the 4S LiPo battery voltage to 5 volts for the sensors and Pico and 13.5 volts for the motor controller. The program I wrote for this is pretty basic and a little bit boring. The 2 biggest parts were the procedure that homes the magazine on startup and the logic that accelerates and decelerates the motors. The magazine homing procedure reads the values of each of the 3 limit switches and the through beam sensor and then moves the magazine from there. This is what that looks like.
Wow!
The motor ramping procedure is used to give the motors enough time to accelerate and decelerate. If you ramp too quickly, you get some problems. I'll talk more about that in a bit. When I finished writing the code and wiring things up, I immediately tested the program and it was perfect.
Nice.
One interesting issue I had wasn't mechanical at all. The motor ramping procedure I wrote worked pretty well, but it was a bit slow. When I sped it up, one of the motors just started to pulsate. Initially, I thought that maybe this motor wasn't getting the proper PWM signal, so I measured the input signal with my oscilloscope and saw that the 2 signals were exactly the same. In case you didn't know, PWM stands for pulse width modulation. It is a method of transmitting data by varying the width of electrical pulses in a square wave. For components like the servo, the width of the pulses correspond to a specific position or angle. For these motor controllers, the pulse width is directly related to the motor speed. Anyway, my next step was to measure the signal with the motors running. Each time the motor pulsed, I saw that it would send spikes of voltage that can be seen on the signal line. PWM signal coming from the Pico is 3.3 volts, and these spikes were adding almost a full volt to the signal. This seemed like a significant amount, so I figured this extra voltage was confusing the motor controller. To try and reduce these spikes, I started adding capacitors to the power supply, the motors, and anywhere else I could think of, but nothing was getting rid of the voltage spikes or the pulsing motors. At a loss for what to do, I decided to hook these motors up to my trusty radio and receiver that I had been using for testing before I was using the Pico. I powered everything on using the same power supply and started moving the motors. I guess I had been accelerating too quickly. I noticed something a little bit strange. If you look at both of the motors, one starts moving before the other. Right now, each of these motors is getting the same exact signal, so why are they moving at different rates? I wanted to know just how fast these motors were spinning, so I went online to find a tachometer. Blown away by the insane price tag, I decided to build my own using my $500 oscilloscope. I zip-tied the LED and photodiode for my sensor experiments and measured the output voltage from the photodiode with the oscilloscope. I taped a piece of aluminum foil to the flywheels, spun them up, and measured the speed, and saw that the motors indeed were spinning at different rates. To fix this issue, you have to calibrate the motor controllers so they respond to the same PWM signal range. Instead of looking up how to do that, I messed around with my tachometer and found which signal ranges for each motor would give me a speed range that I wanted. I chose a nice idle speed of 35 Hz to a max speed of 350. Beyond 350 Hz, the motors vibrate quite a bit. Once I had everything running, I wanted to get it automatically shooting targets as quickly as possible. My original turret makes for a pretty solid base, so I got rid of the unnecessary parts, installed the adapter, hijacked some of the output pins, and slightly modified the code. It's got the same components and program as my old turret, so its ability to track targets still sucks. I'll be fixing this in part 2. With how fast this thing can shoot darts, I decided to switch it from face tracking to color tracking. I was getting tired of constantly shooting myself in the face with my last turret, and I just didn't want to keep risking going blind. Thanks for watching this far into the video. I had a lot of fun making it and have many more projects like it planned. So if you like this video and want to see more like it, please consider liking and subscribing. Thanks.